Welcome back to the deep dive. Today, we're digging into something, well, something that seems simple on the surface, but has layers of complexity underneath.
That's right. We're talking about the two-handed pistol grip.
Exactly. And we're going way beyond just, hold it tight. We're tackling performance, efficiency, the real mechanics of it.
We really are. Forget a lot of the standard stuff you might have read. This is a deep analysis looking at the biomechanics, the kinetics, basically treating the shooter and the firearm as one integrated system.
And our goal today, our mission, if you like, is to explore what the sources we looked at are calling a paradigm shift.
Yeah.
Which sounds dramatic, but it seems fitting.
It really does. Because the old way of thinking just doesn't capture the whole picture.
Right. If you're serious about getting better competition, maybe law enforcement, or even just pushing your own limits, you figure out pretty quickly it's not just about how strong you are.
Mm-hmm.
It's about lining up your body, your anatomy, with, well, the laws of physics, basically.
And that's where the traditional training often falls short. The old model was mostly about simple opposing pressure, right? Just squeezing inward.
Yeah, like holding a brick.
Kind of, yeah. But that misses the point. The big idea we're unpacking today reframes that completely. The optimal grip isn't just a squeeze. It's a really sophisticated, three-dimensional biomechanical vice.
A biomechanical vice.
Yeah.
I like that. And the purpose of this vice is super specific, isn't it?
Absolutely.
We're talking about directing all those muscle forces, those vectors, so they meet, they converge, right at what the source material calls the epicenter of ballistic combustion.
That phrase really jumps out, doesn't it?
It does. It sounds like something from, I don't know, an engineering diagram.
And in a way it is. It's technical because the solution is technical. That convergence point is the absolute key to getting maximum control, maximum speed, minimum disruption.
And just to give everyone listening a sense of the biological complexity we're wrangling here, think about this detail from the research.
Yeah, this is wild.
The human upper limb, so your arm, wrist, hand, it has roughly 54 articulating joints.
54.
54 moving parts that all have to work together. So marksmanship at this level depends on integrating your skeletal alignment, managing all this mechanical resonance
Across all those joints.
during a really violent, super fast kinetic event. It's your body trying to tame this, mechanical explosion.
It fundamentally changes how you think about stability, doesn't it? You're not just holding something still.
No way. You're stabilizing a system with 54 potential points of failure against, what was the pressure figure?
Up to 35,000 pounds per square inch, maybe more in some cases.
Right. Against that kind of force. It's a serious challenge. Okay, so let's unpack this whole thing before we even get into the new technique where your hands go. We need to be crystal clear on the what. What's the job description for the grip?
Right.
From a purely biomechanical view, what does an effective grip actually need to do? Because obviously it's doing a lot more than just keeping the gun from flying out of your hand.
It really is. And the research breaks it down into 4 core functions. But the crucial thing, and this gets missed a lot, is that they are interdependent.
It's interdependent, meaning they all rely on each other.
Exactly. They're not separate jobs you can do one at a time. They form this matrix of required outputs. If you mess up the structure needed for one function, you immediately compromise the other 3.
Okay, that's important. Let's take some time then and define each one. Where should we start? Maybe the most obvious one. Control.
Yeah, let's start there. Function number 1 is the control of angular momentum.
Angular momentum. So, rotational force, like twisting.
Precisely.
Yeah.
When that cartridge goes off, the barrel, the bore axis, is physically above where your hand meets the grip.
Right, there's always that gap.
And that offset creates leverage, huge leverage, actually. That leverage generates torque, a twisting force, and that torque is what makes the muzzle flip upwards. So the primary job of an effective grip is to fight that specific rotation, to apply counter torque and limit how much the muzzle actually rises. It's about controlling that angular momentum.
So if someone's just focusing on squeezing the gun straight back into their body, they might be handling the push, the linear recoil, but they're basically ignoring the flip, the angular part.
You nailed it. You can have a really strong rearward hold, feel like you're locked in, but if your actual biomechanics, your hand and arm position, aren't set up to fight that upward rotation,
The muzzle still climbs.
it still climbs significantly. And that climb wastes time between shots. You end up fighting the muzzle rising instead of addressing the root cause, which is that leverage and torque.
Okay, that makes sense. Function 1. Stop the flip. What's number 2?
Function 2 follows directly from that. It's about the next shot, maintenance of sight alignment.
Getting back on target quickly.
and consistently. This function demands repeatability. It's about ensuring you can get that sight picture back fast after the shot breaks and get it back to the exact same place every single time.
How does the grip achieve that repeatability?
Through structure. If you're correctly using bone and connective tissue, the strong stuff, to bear the recoil load, your hand and the gun naturally want to snap back to the same spot. It's like a spring returning to its neutral position.
But if you're just muscling it.
Right. If you're fighting recoil mainly with small, easily tired muscles, those muscles are going to contract slightly differently with each shot, especially as you fatigue. That introduces variation, inconsistency in your grip, and slows down how fast you can reacquire the sights. You lose that automatic return to zero.
So efficiency in structure leads directly to speed in reacquiring the target. Consistency equals speed.
Precisely. Which brings us to function number 3, and this one is often really misunderstood: energy dissipation.
People think strong grip, just squeeze harder.
Yeah, and while some strength is needed, just strong isn't enough. It's about how that energy is handled.
Why isn't raw muscle strength the answer here? Hands, strong hand muscles can't take that continuous pounding, is that it?
That's exactly it. We have to move beyond just thinking about muscle power. We are talking about distributing an absolutely massive recoil impulse. Remember that 35,000 psi figure?
Yeah.
That creates a huge sudden force. We need to channel that force through the most robust structures we have, our bones and our connective tissues. We simply cannot rely only on the small muscles in the hand, the intrinsic muscles, to absorb that kind of shock repeatedly.
Oh, they just get tired.
They fatigue incredibly quickly. That leads to tremors, maybe developing a flinch, and eventually your whole technique just breaks down if you're shooting a lot of rounds.
So if I'm at the range for a couple of hours or in a competition, my hand muscles are fundamentally not designed for that kind of continuous high-impact shock absorption. The goal has to be making my whole arm, my whole structure, act like a conduit for that energy.
That is the core engineering principle behind this updated grip model. The kinetic energy must be shunted backward efficiently through the biggest, strongest structures available, your skeleton.
All the way back, where?
All the way back to your axial skeleton, your spine, your pelvis, your core. The hands really just become the interface, the crucial connection point that allows this structural energy transfer to happen.
Wow, okay. Conduit, not just a clamp. And the last one, function 4. You said it was neurological.
Yes, the fourth function taps into the brain's role: sensoromotor calibration.
Sensoromotor. Sounds complex.
It's tied deeply to proprioceptive feedback. Proprioception is sometimes called the sixth sense. It's your body's internal awareness of where its parts are, how they're oriented, how they're moving, even without looking.
Like closing your eyes and touching your nose.
Exactly like that. A consistent, optimized skeletal grip allows your body to build a reliable neuromuscular baseline. It creates a fixed map in your brain of exactly what correct grip tension and position feels like.
And why is having that internal map so critical for shooting?
Because it enables a rapid, consistent response for follow-up shots. If your grip changes even a tiny bit from shot 1 to shot 2, the proprioceptive map your brain is using gets corrupted. It gets noisy.
So the brain has to sort of recalculate everything.
Yes, it forces the brain to reassess, introduces lag, and slows down those crucial follow-up shots. But with a stable, calibrated grip, the brain trusts the signals it's getting. It allows for almost subconscious correction and much faster reaction times. You can start recovering during the recoil cycle, not after it.
Okay, that gives a really comprehensive picture. So the grip isn't just holding the gun, it's managing torque to stop the flip, ensuring repeatable positioning for speed, surviving this massive explosive impulse by channeling energy, and providing constant feedback to the brain for calibration.
It's a full-spectrum physical and neurological tool. Every element has to be working.
Right.
So now that we know the 4 jobs the grip has to do, we need to figure out how to build the anatomical structure, the mechanism that can actually perform all 4 simultaneously. And it starts right where the hand meets the gun: skeletal alignment.
And the research is really emphatic about this point, that alignment begins, fundamentally, with the high tang grip.
It's non-negotiable. It's the absolute prerequisite. Getting that high tang grip means pushing the web of your shooting hand, that fleshy part between your thumb and index finger, as high up as possible onto the back strap of the pistol frame.
Right up under the beaver tail, if it has one.
Exactly.
Yeah.
You want to minimize the physical distance between the line of the barrel, the bore axis, and the main bones of your forearm, the radius and ulna.
Why is getting the hand high so critical? What does that height actually do structurally?
It's the origin point for structural support. By getting high on the tang, you physically align your radius and ulna, those two big forearm bones, more directly behind the path of the recoiling slide.
Let's pause on that alignment for a sec.
Yeah.
Reducing the distance, getting those forearm bones lined up with the slide's movement. Why does that specific geometry matter so much?
It boils down to leverage and physics. Think about trying to stop a heavy swinging door. Do you push near the hinges or way out at the edge?
Out at the edge gives you more leverage?
Right, but here we want the opposite. We want to minimize the leverage the recoil has on our arm. If the force from the recoiling slide is even slightly offset, slightly below the long axis of your forearm bones,
It creates a lever arm.
instantly. And that lever arm generates unwanted rotational force, torque. And that torque then has to be fought by smaller, weaker muscles in your wrist and forearm that fatigue really quickly. They aren't designed for massive torque management.
Okay.
But the high tang grip gets those strong forearm bones lined up behind the force. It ensures the kinetic energy transfer is primarily linear, straight back along the bones. This makes the whole system structurally sound, like a solid post taking a direct hit. You want to channel the force linearly, not fight it rotationally.
Got it. So we're turning the forearm into a stable beam, basically, designed to transfer force straight back, rather than letting it become a lever that encourages the gun to twist or flip.
That's a perfect way to put it. The bone provides the structure, the rigidity. Now the muscles, their job is to stabilize that structure, which brings us to muscular engagement, the active vice. And this isn't just squeezing randomly, it's about applying specific isometric tension in very targeted muscle groups to support that bone alignment.
Isometric meaning the muscle creates tension without changing length, like bracing.
Exactly, like bracing, holding firm. So which muscles create that initial solid connection between the hand and the gun?
That foundational grip.
That's the compression component. It secures the gun front to back along the anterior-posterior axis. This pressure comes mainly from the thenar and hypothenar eminences.
Those are the meaty pads on your palm, base of the thumb and the outside edge.
That's them, the big fleshy parts. They provide a large, robust contact surface area. That large surface generates friction and stability. If you watch really high-level shooters, you see their entire palm surface seems engaged, maximizing that contact. It's not just fingertips.
So if someone feels like they're mostly gripping with their fingers, like pinching the gun,
They're missing the entire foundation. The fingers provide crucial support, absolutely, but the primary stabilizing pressure, the anchor, comes from those palm pads making full contact.
okay, foundation set. What muscles keep it stable during the shot?
Now we need the muscles for sustained isometric control. These are primarily the deep forearm flexors, the ones that keep your wrist angle locked and prevent it from breaking down under recoil. We're talking about the flexor carpi radialis.
That runs along the thumb side of the forearm.
Yes, it's crucial for preventing the wrist from extending backward or collapsing inward. Then there's the flexor digitorum profundus, which controls the deep flexion of your fingers, keeping them wrapped consistently. And very importantly, the pronator teres.
Pronator teres. That muscle helps rotate the forearm, palm down, right? Why is that involved in gripping?
Because it fights the opposite rotation. Under recoil, the gun might try to twist or rotate in your hand. The pronator teres helps lock the forearm rotationally, preventing that twisting motion. It contributes significantly to rotational stability.
So these muscles maintain that fixed wrist angle, keep everything aligned throughout the whole violent cycle.
They brace the structure. Then finally, for actually absorbing and damping the recoil impulse itself, we need the opposing muscle groups. This is recoil damping and wrist locking. And here we engage the extensor carpi radialis longus and the brachioradialis.
Okay, the extensors. Those are on the top side of the forearm, the ones you use to pull your hand back towards your elbow.
That's right. They provide the essential countertension. Imagine pulling a rope taut from both ends. The flexors are pulling one way, the extensors are pulling the other. This co-contraction makes the entire wrist and forearm unit incredibly rigid.
Like preloading the structure.
Exactly. It ensures the kinetic chain stays unbroken and ready before the high impulse phase of recoil hits. If these extensor muscles relax even slightly, the whole skeletal structure can momentarily collapse, and the job of absorbing energy shifts disastrously back onto those smaller, weaker muscles and connective tissues.
This detailed breakdown is fascinating. It's not just grip hard, it's specific muscles doing specific jobs. The palm pads for the friction base, the flexors and pronator for maintaining the angle and rotation, and the extensors for providing that critical countertension and damping.
Precisely. But even this incredibly strong hand and forearm structure needs to be anchored to something solid, right?
Otherwise, the whole arm just moves.
Exactly. We need to complete the chain. We need the upper kinetic chain anchor. All that force being channeled back through the forearm bones has to go somewhere efficiently. If your shoulder is loose, slumped forward, or unstable.
The energy transfer just stops there, or gets absorbed inefficiently.
Both. It creates a weak link. The energy dissipates poorly, causing the shooter to absorb more impact in the shoulder joint itself, and it results in unnecessary muzzle movement because the base isn't stable.
Okay, so how do we create that solid anchor at the shoulder? What's the technique?
It's achieved through scapular retraction. This is a conscious action. Pulling your shoulder blades, your scapulae back towards your spine and slightly down.
Engaging those big back muscles.
Yes, primarily the rhomboids and the trapezius muscles. This action effectively locks the entire shoulder girdle, making it a stable platform.
I can definitely imagine shooters focusing so much on their hands and arms that they completely forget about their shoulders and back.
It's incredibly common. But if the shoulder is unstable, the whole system built below it becomes unstable no matter how good the grip itself is. Locking the scapula does something critical. It prevents the humerus, your upper arm bone, from becoming a point of uncontrolled rotation or movement relative to the torso.
So it keeps the upper arm fixed.
Relatively fixed, yes. It ensures that the force absorption route remains clear, linear, and predictable. The energy travels up the rigid forearm, through the locked elbow joint, up the humerus, and is then anchored by that stable scapula, leading the force directly back into your body's core, the axial skeleton. Without that sophisticated anchor point, the entire grip structure, no matter how well executed with the hands, just breaks down. It becomes a much less efficient, muscle-driven system again, prone to fatigue, inconsistency, and ultimately lower performance, especially when you shoot a lot. You're essentially trying to turn your entire torso into the ultimate shock absorber.
Okay, this detailed anatomical foundation really sets the stage for understanding the core of this paradigm shift we mentioned.
Right.
We've established that the old way, the traditional doctrine, was heavily focused on just simple lateral opposition, squeeze inward from the left hand, squeeze inward from the right.
Like a clamshell, basically.
Yeah. And the research we're looking at says that's just, well, it's insufficient, it's incomplete, because it doesn't properly align the force you're applying with the actual mechanical movement happening inside the firearm during recoil.
That's the key flaw. Traditional grips might give you decent side-to-side stability, but they often do a poor job of managing the vertical angular momentum, the muzzle flip, and also the longitudinal displacement, the gun moving back and forth. The updated model specifically targets the internal physics of the gun.
Okay, so let's get into the specifics of the new vector model. If that simple inward squeeze is wrong, or at least incomplete, where should the force from both hands be directed? Where are they supposed to meet?
There's a common critical target point for both hands. The sources call it the ballistic epicenter.
The ballistic epicenter. We need to define that precisely. Where is it on the gun?
Think of it as the geometric center of the energy release. It's generally located at the junction between the barrel and the slide, often slightly forward and high up on the frame, right around where the chamber area is.
Okay, so near the top front part of the frame.
Pretty much. And the critical principle is every ounce of purposeful muscular force you apply with both hands needs to be directed towards that single specific point. They must converge there.
Converge. Like lines meeting at a point.
Yeah.
That sounds incredibly precise, almost difficult to visualize and actually do correctly. How does the dominant hand, the trigger hand, contribute to this convergence? What's its force vector?
This is where it gets really different from traditional teaching. The dominant trigger, hand vector, exerts pressure that is primarily forward and slightly upward.
Forward, not just back into the hand.
Forward and slightly up. This is a radical departure from just thinking about a rearward or inward squeeze. That forward vector is critical because it directly preloads the frame against the impending rearward acceleration of the slide. It braces for the impact.
And the slight upward pressure.
That helps counteract any downward pressure or rotation that might be induced by the trigger finger movement itself, and also helps oppose the initial downward torque from the high bore axis. But the main direction is forward, aimed right at that ballistic epicenter.
Okay, wait a minute. If my trigger hand is pushing forward, how do I stop myself from just pushing the whole gun forward off the target? Or messing up my trigger pull, which needs isolation? That sounds like a recipe for inconsistency.
That's an excellent point, a really practical challenge, and the answer lies entirely in the support hand. The forward pressure from the dominant hand isn't meant to create movement, it's isometric tension.
Ah, bracing again.
Exactly. It's establishing tension within the system, holding it firm before the shot breaks. If you do it right, and yes, this takes dedicated, consistent practice, that tension is set and held constant. Critically, the force comes from the meaty parts of the palm and the base of the fingers applying that compression.
Right, the thenar and hypothenar eminences we talked about.
Yes. While the trigger finger itself maintains its necessary isolation and independent movement, you're essentially pushing the frame forward, getting it ready to absorb the slide's counterpush.
Okay, that makes more sense. It's tension, not a shove. So the support hand has to provide the counterforce to lock everything together. What's the vector for the support hand? Where does it push or pull?
The support control hand vector is where a lot of the real work in controlling recoil happens in this model. It exerts a very strong counter pressure that is directed upward and inward.
Upward and inward.
Yes. It originates primarily from the area contacting the base of the trigger guard and also strongly from the heel of the support hand palm, where you have that large contact surface against the grip panel.
And that upward force is the main component fighting muzzle flip.
It's a huge component, yes, direct opposition to the flip. The inward force provides that necessary side-to-side medial-lateral compression we still need for stability. But the key is that this combined upward and inward vector also terminates precisely at that same focal point, the ballistic epicenter. It directly counteracts the dominant hand's forward-upward tension.
So it's not just left versus right anymore. It's like the dominant hand pushes forward up towards the epicenter, and the support hand pulls sort of back up in towards that same epicenter, creating this focused tension right where the action is.
You could almost visualize it like a kinetic tripod, maybe. 3 points of interacting tension meeting at that critical spot. That description captures the essence of it, focused convergence.
And what's the payoff? What does achieving this convergence actually do for the shooter?
The result is a massive leap in functional efficiency. Because the applied muscular forces are now precisely aligned with and directly opposing the actual forces of recoil, the rearward push and the upward flip generated by the cartridge detonation.
The energy goes where you want it to go.
Exactly. That alignment converts that violent, somewhat chaotic recoil energy into predictable, distributed load paths. Paths that are absorbed efficiently by the skeletal structure, the system we just built in the last section, instead of being randomly fought by small muscles pulling in less effective directions.
Okay, let's translate that into results on the range. What are the immediate performance outcomes? If a shooter really learns and applies this convergence model, what differences will they actually see and feel?
The improvements are usually immediate, tangible, and measurable. Number one, and maybe the most obvious, reduced muzzle climb.
Flatter shooting.
Much flatter. Because those opposing force vectors are converging right where they need to be to directly counteract the rotational force, there's simply less rotational energy left over to make the muzzle rise. The gun tracks flatter during the firing cycle.
And a flatter trajectory means the sights don't have as far to travel to get back on target.
Precisely, which leads directly to benefit number two, faster sight recovery. Because the force absorption is now more linear and symmetrical, straight back into the aligned skeleton, and then straight forward as the slide returns, the firearm tends to return to its pre-shot point of aim much more repeatably.
Less wobble.
Way less lateral wobble or random drift that you often see with less structured, more traditional grips. It cycles straight back, straight forward. That drastically cuts down the time needed to get a follow-up sight picture and make an accurate shot.
And for someone who shoots a lot, training classes, practice, competition, maybe the biggest practical benefit is just being able to shoot longer without breaking down.
Absolutely. That's outcome number 3. Decreased cumulative fatigue. This is huge.
Right.
By redirecting the recoil energy dispersion so it utilizes the large, robust, load-bearing structures of the skeleton,
Jones and joint.
you spare the small, easily fatigued motor units in the hands and forearms. They aren't bearing the brunt of the impact anymore. This dramatically extends your performance endurance. You stop relying so much on vulnerable muscle tissue and start relying on bone geometry and structural alignment, which fundamentally don't tire in the same way. You can maintain peak performance for much longer. Now, to really cement this whole concept, it helps to shift our thinking one more step. We need to encourage you, the listener, to stop visualizing the pistol as just an object you're holding on to.
Okay. How should we visualize it instead?
You need to visualize it as a dynamic six-sided kinetic system. Think of it like a box floating in space.
A box. Okay.
When that gun fires, there are forces trying to make it move in every possible direction. It wants to translate, move linearly forward, back, up, down, left, right, and it wants to rotate, twist around all three of those axes as well. That's 6 degrees of freedom for potential unwanted movement.
Right. 3 dimensions of linear movement, 3 dimensions of rotational movement, 6 axes total.
Exactly. A truly perfect grip needs to apply constraints across all 6 of those potential axes of movement simultaneously. It has to minimize both the translational displacement and the rotational displacement. It needs to lock that box down in space.
A complete 3-dimensional lockdown. That sounds comprehensive.
It has to be. So let's do a detailed breakdown of how the two hands work together using those converging vectors we just discussed to create this biomechanical vise. We need to look at the 3 critical pairs of opposing planes of force that achieve this total 6-axis stabilization.
Okay, 3 pairs of opposing forces. Let's start with the vertical axis. Superior, inferior, up and down. This is mostly about fighting that muzzle climb, right?
Primarily, yes. This vertical control is achieved by that wrist locking. We talked about the co-contraction of the forearm flexors and extensors creating rigidity combined with the specific vectors.
How do the vectors play in here?
The dominant hand's forward and upward vector provides upward pressure on its side, supporting the frame from below, in a sense. Then, crucially, the support hand's upward and inward vector provides the counterforce, the superior constraint, pushing up from underneath the trigger guard area.
So one pushes up from the back top, the other pushes up from the front bottom.
Essentially, yes. The convergence of these 2 opposing upward force components locks the entire wrist joint complex against that massive vertical rotational force induced by recoil. Think of it like trying to immobilize an object by pushing firmly against its top surface and its bottom surface at the same time.
You create a vertical clamp, and the instant that tension relaxes, even slightly,
the gun is free to rotate vertically. The lock breaks. Now, what about side-to-side stability? Medial lateral, preventing twisting or yawing.
This sounds more like the traditional squeeze.
It incorporates that element, but integrates it. This is achieved by inward compression, which the sources call the clamshell effect. But it's not just an inward squeeze, it's directed inward towards that epicenter.
How is it applied?
The thumb pad of the dominant hand presses inward, say left for a right-handed shooter. The heel and palm surface of the support hand presses inward from the other side, right? This creates a uniform, balanced inward pressure.
And the goal here is?
Maximal frictional stability. This prevents the pistol frame from twisting or rotating within the hand's resisting yaw and roll, especially during the violent cycling of the slide or if you're shooting very rapidly. It keeps the gun aligned laterally.
Okay, vertical locked, sides locked. What's the last pair, the long axis?
Yes, the axis that runs along the barrel. Anterior, posterior. Front-to-back movement, which aligns perfectly with the main direction of the recoil impulse itself.
How do we control movement along that axis?
This longitudinal control comes from that push-pull tension we introduced with the vectors. Some sources call it the nutcracker effect.
Push-pull. Reminding me again.
The dominant hand exerts that slight isometric forward pressure, establishing constant forward tension against the frame. The support hand provides the rearward countertension, actively pulling back slightly against the frame, often with the fingers wrapped around the front strap or trigger guard.
So one hand pushes forward, the other pulls back, creating tension along the gun's length.
Exactly. This establishes a preloaded, fixed length for the entire handgun kinetic chain before the shot even breaks.
And having that fixed length, that pre-tension, is key. Why?
Absolutely critical. It means there's no slack, no give in the system along the recoil axis that the initial impulse can exploit or take up. This tension does 2 crucial things. 1, it helps the structure absorb that initial sharp rearward jolt more effectively. And 2, it maintains a consistent depth of engagement between the hands and the frame, ensuring your hands are pressed into the gun the same way, with the same pressure every single time you grip it. Consistency again.
Wow. The synthesis here is really powerful. When you put all 3 pairs together, the vertical lock, the medial lateral clamshell, and the anterior posterior push-pull.
You transform your hands from just something holding the gun into a truly balanced, dynamic, 3-dimensional vise.
Applying uniform controlled pressure across all 6 opposing planes at the same time.
And that simultaneous multi-axis application is the secret sauce. You need control across all three spatial dimensions, forward, back, up, down, left, right, plus the rotations around those axes to minimize all that potential displacement during the incredibly brief, incredibly violent firing cycle. Any weakness, any lapse in control in one dimension immediately compromises stability in the others.
It really is a structure designed specifically to survive and control an explosion happening right in your hands.
That's exactly what it is, taming the explosion through biomechanics.
Okay, this is starting to make a lot more sense. We've built the external structure, this biomechanical vines with converging forces. Now we really need to connect that external technique to what's actually happening inside the firearm.
Right, the why behind the how.
Exactly. What is going on mechanically, physically inside that pistol that our carefully constructed grip has to counteract?
To understand that, we have to look at the internal explosion itself and how momentum gets generated. When the firing pin hits the primer, the powder ignites almost instantaneously.
A controlled burn, but very rapid.
Extremely rapid. Combustion gases expand incredibly quickly, generating enormous chamber pressure. As we mentioned, for typical pistol calibers, this pressure spikes somewhere in the range of 20,000 to maybe 35,000 pounds per square inch PSI.
Just to reiterate that scale, that's like 10 times the pressure in your car tire, focused in that tiny brass case.
It's immense, and as those gases push the bullet forward down the barrel at high speed, Newton's third law comes into play immediately.
For every action, there's an equal and opposite reaction.
Precisely. The forward momentum imparted to the bullet and the expanding gases generates an equal and opposite momentum acting rearward. This momentum is what drives the slide assembly backward against the frame. That is the fundamental recoil impulse that the shooter ultimately has to manage.
Okay. And the sources we looked at break down how that recoil energy gets transferred to the shooter over time. It's not just one single push, as it happens in phases.
That's right. It's a dynamic process. Understanding these three phases of dynamic recoil load transfer is key because the timing dictates how the shooter's grip needs to respond.
Let's break them down. What's phase I?
Phase I is the combustion impulse. This is the initial, very sharp, almost instantaneous jolt. The rearward acceleration from the pressure peak is transmitted directly from the bore axis through the barrel and frame structure straight into the shooter's dominant hand via the grip.
So this is the first hit the hand feels.
Yes. It happens incredibly fast. We're talking microseconds. It's perceived as that initial sharp kick or jolt. The rigidity established by the dominant hand's forward tension, part of that push-pull, is what primarily absorbs and resists this very first hit.
Okay, initial jolt absorbed. Yeah. Then the gun's internal machinery starts moving.
Exactly. That leads directly into phase II, spring compression. Immediately following that initial impulse, the slide starts accelerating rapidly rearward, moving relative to the frame. As it moves back, it pushes against the recoil spring,
which starts to compress.
Right. And as that spring compresses, it starts storing enormous amounts of elastic potential energy, like stretching a rubber band. And here's a really crucial technical detail, something that makes modern semi-automatics manageable compared to, say, a simple blowback gun or a rigidly locked system. This spring compression phase temporarily decouples the slide's momentum from the frame's inertia.
Decouples. Explain that. What's decoupling mean here?
It means that for a brief moment, the full rearward momentum of that heavy slide isn't being transferred directly and instantaneously to the frame, and therefore to the shooter's hand.
Oh, the spring acts like a buffer.
Exactly. The spring absorbs that initial violent momentum of the slide over a slightly longer period of time as it compresses, converting the slide's kinetic energy into stored potential energy within the spring itself. This brief moment of decoupling is critical. It effectively spreads the recoil impulse out over time, making it feel less sharp.
If the slide and frame were locked together and moved back as one single unit,
the peak felt recoil force would be punishingly high, much higher. That spring action smooths it out. But it also means the shooter's body, which reacts much slower than these mechanical events, has a tiny window to maintain stability while the spring is doing its work.
So does that mean really good shooters are almost subconsciously timing their stability, their muscle tension, based on that spring dynamic? They aren't just reacting after everything stops moving?
That's precisely the goal of developing that kinesthetic map we talked about. Your kinetic chain, your whole grip structure, has to maintain that perfect isometric hold during the spring compression phase.
Why is stability during compression so important?
Because if you relax even slightly, if your grip wobbles while those internal forces between the slide and spring are peaking, the gun's alignment will be disrupted right at the most critical moment. The sights will wander unpredictably.
Okay, so maintain the vice grip through phase 2, which sets up the final phase, which can also mess up your sight picture if you're not ready.
Yes. Phase 3, the restorative phase. Once the slide reaches its maximum rearward travel, hitting the stop on the frame, that fully compressed recoil spring immediately starts to decompress rapidly.
Bringing back.
Right. All that stored elastic energy is converted back into kinetic energy, but now it propels the slide forcefully forward. This forward motion strips the next round from the magazine, chambers it, and slams the slide back into battery, returning the whole system to mechanical equilibrium, ready for the next shot.
But that forward slam also creates a force the shooter has to deal with.
Absolutely. The shooter must maintain that same vice-like grip, that push-pull tension, to resist this forward impulse. If the grip relaxes as the slide comes forward, the muzzle can dip downwards noticeably as the slide slams shut.
So the shooter's role, then, is to provide this unwavering platform, this isometric stability, against 3 distinct rapid-fire oscillations. The initial rearward jolt, the continued rearward acceleration of the slide during spring compression, and the final forward restorative motion of the slide returning to battery.
That's it perfectly. The shooter's grip must provide isometric stabilization, that fixed, non-moving tension established before the shot to counteract this entire complex, multi-stage oscillation, if they do that correctly.
The sights track smoothly.
Yes. It allows the entire upper kinetic chain, hand, wrist, arm, shoulder, to function as a cohesive, dynamic shock absorber that facilitates that rapid, linear sight return we're always chasing. The sight should ideally track slightly up during recoil and then come immediately straight back down along a consistent vertical plane with minimal wandering.
Okay, to make that whole system work, to ensure the energy goes where we want it into the skeleton, let's revisit that load path sequence. How does the energy travel from the hand back to the core? You mentioned something specific about the elbow locking.
Yes, the integrity of the load path is everything. This sequence is the designed linear pathway for distributing that recoil impulse, making sure the strong bone structure bears the load, not the smaller, vulnerable muscles. It starts right at the metacarpal interface, the connection between the bones of your hand and the bones of your wrist.
Hand to wrist.
The energy then transfers directly into the 2 large forearm bones, the radius and the ulna, through that now rigid wrist joint.
Okay, up the forearm, now the elbow. How does the energy get past the elbow joint without causing the arm to bend or rotate unpredictably? That seems like a potential weak point.
It is a potential weak point, if not managed correctly. The energy travels directly into the humeral nard joint, the main hinge of the elbow. But it's stabilized by what the biomechanics sources refer to as olecranon locking.
The olecranon locking. What's that?
The olecranon process is the bony point of your elbow, the part you bump, the funny bone area. The olecranon fossa is a matching notch in the humerus, your upper arm bone. By keeping the arm relatively straight, not hyperextended and locked out painfully, but fully braced and extended, these bony structures engage more fully.
They sort of seed into each other.
Exactly. The bone shapes lock together, creating a much more rigid connection through the elbow joint. This effectively channels the recoil force straight up the humerus, rather than allowing the elbow to flex or wobble.
So the elbow stops being a flexible hinge and momentarily becomes more like a solid, fixed joint in the structural chain.
Precisely. That rigid, locked structure then carries the energy up the humerus, straight to the scapular anchor, that retracted, stable shoulder blade we discussed, and from there, the remaining energy is safely distributed down into the large mass of the torso and the spinal base.
It's a complete sequential linear pathway.
Yes, and following that path converts that sharp ballistic impulse into a predictable, distributed joint load, effectively bypassing those vulnerable, fatigue-prone muscles almost entirely. It's what makes the shooter's body resilient and the performance repeatable, shot after shot after shot.
This is really comprehensive. We've covered the immediate performance gains, flatter shooting, faster recovery. But what about the long haul? For someone who shoots a lot, maybe trains seriously, competes. What are the long-term payoffs neurologically and physically for adopting this kind of advanced structured technique?
The long-term benefits are arguably just as important, if not more so. The most profound change happens in the brain and nervous system, neuromuscular adaptation.
The brain learns the technique.
It does more than just learn it, it optimizes it. As a shooter consistently applies this optimized skeletal alignment and these specific force vectors, the brain starts to recognize a pattern. It sees that the incoming sensory signals the feeling of the grip position, the precise tension levels are identical or very nearly identical, shot after shot after shot.
And that consistency allows the brain to, build a better program.
Essentially, yes. It allows the brain to map and then encode the required motor response with incredible precision.
Which part of the brain is handling that complex motor learning?
The cerebellum, located at the back of the brain, is the master coordinator for this kind of thing. It learns and encodes the exact degree of isometric tension needed in each muscle group, the precise amount of scapular retraction required, the optimal joint angle coordination through the wrist and elbow, all the elements needed for perfect recoil management.
And this becomes automatic.
Over time, yes. It transitions from something you have to think about consciously, step by step, into an automated, deeply ingrained motor pattern. That automation is what allows you to perform effectively even under high stress.
And the result of that deep encoding, that automation, is what's called kinesthetic mapping.
Exactly. That's true muscle memory, built on proprioception. It allows the shooter to bring the gun up and find the sights or realign the sights after recoil, almost subconsciously.
Alignment by feel.
That's the phrase you hear competitive shooters use, and this is what they mean. Even when they're under immense physiological stress, maybe their heart rate is pounding due to competition pressure, or, in a defensive scenario, an active threat, their body knows where the gun should be relative to their eyes and their body posture. They aren't relying solely on slow, deliberate visual confirmation. The brain trusts the feel, the proprioceptive input from that consistent grip.
That sounds like a huge advantage under pressure. And the sources we looked at even had some numbers to back up the efficiency gains from this kind of adaptation, right?
They did. They cited electromyographic studies, EMG studies, which measure electrical activity in muscles. These studies found that consistent training using these optimized principles can reduce co-contraction variance among the key forearm flexor and extensor muscles by as much as 25%.
Co-contraction variance. What exactly is that measuring? Muscles fighting each other?
That's a great way to put it. It's essentially measuring inefficiency, wasted muscular effort, where agonist and antagonist muscles might be receiving slightly conflicting signals from the brain, or just aren't perfectly synchronized, causing them to work against each other unnecessarily.
So if you could listen to the muscles working, an untrained or inefficient shooter might sound like a bit of an argument.
Yeah, a noisy signal.
While a highly trained shooter using this method sounds more like a smooth, coordinated symphony.
That's a very apt analogy. Reducing that internal muscular noise or variance by a quarter leads to significantly smoother, more efficient energy absorption. It eliminates micro-wobbles and speeds up target reacquisition because the whole system is working together harmoniously with less internal resistance.
Okay, smooth operation, faster performance, less fatigue. Now let's shift to the really serious side of this, biomechanical sustainability and injury prevention. What are the real physical risks of sticking with an incorrect, less efficient grip model over the long term, especially for people who put a lot of rounds down range every week or month?
The risks are substantial, unfortunately, and they can often be career-ending or hobby-ending for serious shooters. An incorrect grip, particularly one that relies too much on that simple lateral squeeze, or maybe uses a low tang position that induces more torque.
It puts stress in the wrong places.
Exactly. It induces constant, localized, unnatural torque and stress on vulnerable structures in the wrist and forearm. This chronic repetitive stress specifically targets areas like the narrow passageway of the carpal tunnel, the pronator teres muscle we mentioned earlier, and the extensor retinaculum, which is the band of connective tissue over the back of the wrist that holds the extensor tendons in place.
Those sound like the classic spots for repetitive strain injuries in sports that involve fine motor control and impact.
They absolutely are. That constant strain can lead to chronic inflammation, tendinitis, and even nerve impingement issues like carpal tunnel syndrome over time. Very painful, very debilitating.
So how does the optimized skeletal vector model help prevent this?
In sharp contrast, the benefits of skeletal vector alignment are primarily protective. By deliberately channeling that recoil impulse through the large, robust bone structure and utilizing the bigger muscle groups for stabilization rather than direct absorption.
You take the load off those small, vulnerable tissues.
Precisely. You drastically reduce the localized stress, the repetitive microtrauma that leads to these chronic overuse conditions.
Can you name some specific conditions that this proper alignment helps shooters avoid?
Sure. We're talking about significantly mitigating the risk of conditions like medial epicondylitis, that's often called golfer's elbow, even though shooters get it too. It's inflammation right at the inner point of the elbow where the forearm flexor tendons attach, often caused by excessive gripping force and rotational stress.
Okay, what else?
It also helps prevent various forms of severe wrist tendinopathy, which is just chronic tendon pain and degeneration from that constant lateral stress. And perhaps less obviously, it can even reduce the risk of shoulder problems like glenohumeral impingement.
How does grip affect the shoulder?
Because if the grip and arm structure aren't stable and efficient, the shoulder often tries to compensate with excessive reactive tension to stabilize the whole system. But with the properly locked scapular anchor and linear force transfer, the shoulder doesn't need to tense up excessively, it just acts as a stable base.
So if the load path is clean and direct all the way back, the muscles only need to do their intended job, stabilize the structure, rather than actively fighting misdirected forces. And that saves the joints further up the chain.
You got it. The conclusion here is really important. This optimized group model isn't just about shaving fractions of a second off your split times, though it does that too. It's a fundamental investment in your long-term musculoskeletal longevity as a shooter. It allows you to enhance your peak performance while simultaneously protecting your body against the chronic injuries that so often derail high-volume training and participation in the shooting sports. Perform better, last longer. #tag outro. So, to really bring this entire deep dive together for you, the listener, the core message is that the fundamental approach, the methodology for achieving optimal pistol control, has genuinely evolved. It has to. Yeah. We really need to move past the older, often inefficient traditional ideas based on simple lateral opposition, just squeezing inward. The new paradigm is about understanding and implementing a system of deliberate force convergence.
Aiming those forces right at the gun's ballistic epicenter.
Precisely. It's about consciously integrating your own anatomy, your 54 joints, your specific muscle groups like the rhomboids and pronator tears, with the unyielding demands of physics, specifically Newtonian mechanics happening inside that firearm. It's human anatomy meeting mechanical physics.
So wrapping it all up, what does this really mean for you listening right now? This optimized grip model, built on skeletal alignment and force convergence, aims to achieve 4 key things, all with maximum efficiency. First, minimize muzzle deviation, less flip, flatter shooting. Second, faster sight recovery, getting back on target quicker. Third, dramatically reduced cumulative fatigue, shooting longer and better. And fourth, maybe most importantly for the long run, essential protection against chronic injury.
It requires a mental shift. You have to stop thinking about the firearm as just a passive object you hold on to.
And start treating your hands, your arms, your shoulders, your core as a highly tuned, dynamic structural system.
A system that is intentionally and precisely aligned with the pistol's violent internal split-second mechanical cycle.
Right. And the science on this isn't standing still, is it?
Not at all. The sources we consulted suggest that future research is definitely heading towards using even more advanced tools. Things like high-speed motion capture systems, more refined EMG analysis to quantify even subtler factors. Like measuring the exact reduction in microtremors in the hands, or mapping the load distribution across joints with even greater precision, all achieved by these rigorous, vector-aligned gripping methods. They're constantly refining that interface between the human operator and the mechanical tool.
Which leaves us with, I think, a really provocative final thought for you to consider. If we can analyze and optimize musculoskeletal efficiency down to the millisecond, down to specific force vectors, in something as specialized as firearms control. Think about how profoundly understanding kinetic load paths, force vector alignment, and structural bracing impacts training efficiency, performance potential, and injury prevention in literally any physical discipline you might pursue.
Absolutely. It doesn't matter if it's golf, tennis, weightlifting, throwing a ball.
Right. Whether you're trying to perfect a golf swing, optimize your form on a heavy lift like a clean and jerk, or throw a perfect spiral with a football. The fundamental principles are the same. The human body is the ultimate performance machine. Learning how to align it with physics, how to optimize its structure to manage force. That might be the single greatest key to unlocking lasting high-level mastery, whatever your pursuit.
Well said. It's about working smarter, using the structure you have.
Absolutely. Something to think about. That's all for this deep dive. We'll talk to you next time.